Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. This is our 11th week and we are in first lecture. In this week, we are going to continue our discussion on water tank design, and our aim is to consider a special type of water tank that all of us we are familiar with. As you can see on the picture, we have this type of water tank commonly used, and this is called Intze tank. Right. Now, these are large capacity tanks which is having different structural components, and there is very specific purpose of building that. As we progress in this course, you will immediately see what are the advantages of using this type of tank, particularly when we need to store large volume of water for municipal areas, for townships, and for a bigger locality. Now, it has a cylindrical wall. As you can see, here is the cylindrical wall. And then on top of that cylindrical wall, there is a cover. And then at the bottom also, there is a cover. And it has a sloped boundary near the bottom. It was developed by a German engineer named Otto Intze, and hence it is called Intze tank. Now, in this tank, the main idea is to use membrane shell, okay, that minimizes the bending moment, okay. So, we'll see in a minute what are the different stress components acting. But because of the use of this type of particular geometry of the structure, this tank is very popular for large water storage tank. And for that, again, we have a dedicated code, as you can see, IS 3370. We have used this code earlier also. So we will continue using that code in our design. Now, before we go into the details of structural stresses against which we have to design and provide some reinforcement, let us see first the need for this tank, why we go for this tank. So, as I have already told you, for large capacity, we can provide adequate hydraulic head because these tanks are located at a particular height, and then gravity alone will be sufficient enough for the distribution of water in a township. That's the reason this type of tank is preferred for larger community. So, of course, when it is dedicated for a small township or a locality, it must have the storage capacity for the entire locality, and hence normally these are ultra large tanks. Now, not only this gravity head that it provides, and the distribution is done using free flow of the water, there are some economy of constructing this type of water tank compared to any other type of tank that we have discussed. If you recall, we have discussed rectangular tanks and circular tanks, but this type of Intze tank are economical for large storage capacities, right? Now, from these basic functional requirements, let us move over to the structural behavior of this tank. Now, the geometry that it adopts, it provides uniform stress distribution, because you can see there is a dome at the top, and then there is a circular part, then this inclined part, which are all symmetric about their center line, and we have uniform stress distribution. And it reduces the bending compared to flat bottom tank. Obviously, if you have a tank like this, and just imagine if you have a set of columns holding this tank for large capacities, this plate will behave like this way, and there is a chance of getting huge amount of bending stress and shear stress, which is otherwise not present here. Not to that extent, it is reduced by a significant amount. And of course, because this stress is uniformly distributed and it is reduced compared to flat bottom tank, the material is judiciously used, and there is a certain economy of using this type of geometry so far the material usage is concerned. Now, again, let us quickly revisit the purpose of this elevated tank. The main purpose is, if you have say a pump house here, and if you just fill the tank, then for a township, this water naturally flows down because of this head already available at this tank, and it can provide a continuous water supply. And that's the reason these type of tanks are preferred for municipalities. Beyond that, there is a balanced peak demand and pumping rate that can be maintained for this type of high capacity tanks for a larger area. Now, you can imagine once the tank is filled, then obviously it will have the maximum head available when you allow it to freely flow down through the pipeline and go to the distribution network. But at least because of this height, when it maintains that minimum height, so minimum pressure is always available in the distribution pipeline. And that pressure is sufficient enough to reach at each and every door to which this tank is providing water supply. Now, beyond that, these tanks are also designed to hold the volume of water for emergency usage. For example, fire demand, right? And also, it has additional capacity in case of pump failure, so that the sufficient time is there for maintenance, and during that period, the tank can provide naturally water supply to the community. Now, the question is, why this form of tank is economic? The reason is the use of conical shell, which reduces hoop tension on cylindrical wall. So you can see these are the cylindrical walls, this region, and on top of that the cell structure is there. So that reduces the stress. Second thing is there is a bottom dome here. This bottom dome converts bending into compressions. I have already explained to you, if you have a flat bottom and if you fill it with large amount of water, which will provide uniform load over this slab, obviously this slab thickness will be more because of the bending. Now here, because of this conical shape, then when you fill it up, it behaves like an arch, and therefore the demand for the bending moment is less compared to flat bottom. Then there are ring beams here, one ring beam, another is here at the top. Ring beams resist horizontal thrust effectively. So the purpose of these ring beams are to provide sufficient resistance against horizontal thrust. And the structural action primarily is due to the membrane like structure, so it lowers the reinforcement requirement. So all these together provides a economical usage of material for this large capacity tank. Now, a quick comparison with other type of tanks that we have already considered: circular tank, rectangular tank, and now this week we have Intze tank. So different parameters for comparison: stress behavior. For circular tank, high hoop tension, we have already gone through the examples. For rectangular tank, high bending. But for Intze tank, mostly membrane stress. And that's where the advantage comes. Then the material consumption for circular tank, which is moderate. For rectangular tanks, it is very high, and out of all three combinations, Intze tank has low, and hence it is economical compared to other options. Bending moment, it is significant in case of circular tank. Rectangular tank, it's really very high, and in case of Intze tank, it is minimum. Then of course, suitability. So for small to medium capacity, we can go for this circular tank. For individual household, we can go for rectangular tank, we are very much familiar with. But for a large community, we have to go for this type of tank, which is the Intze tank. Now, of course, you can see the picture on your screen. It has different components, particularly this sloped surface. Then there is a dome at the bottom, there is another dome at the top, a cylindrical portion along with ring beams. So the construction complexity is really more compared to other form, for example, circular or rectangular tank. Rectangular tank is the simplest one. You can construct just 4 walls that will provide a space for water storage. But for this tank, of course, it has different structural components which will offer some amount of construction complexity. But once it is constructed, this is structurally more efficient compared to the other form. Now, let us quickly see what are the different structural components we have in case of Intze tank. As you can see on this schematic diagram, the different structural components are marked. So, the first one, we have a top dome here. This dome provides a cover. Then there is a ring beam here, as you can see. This ring beam actually connects top dome and the side walls. So it's a cylindrical wall here. That side wall is connected through this ring beam. Then there is a bottom ring beam also that connects the cylindrical wall and the conical shell. Okay, here. So the fifth segment is the conical shell, and then there is a spherical dome at the bottom. Now, there are circular girders that holds the column which is marked by 8. So there may be 4, 6 or more number of these columns. So these columns are supported by are connected by these circular girders, and then sometimes bracings are also provided. So these are the different structural components. Of course, we are familiar with the design of this beam and columns. So in our course, we are not going to revisit the beam and column design. That you can easily complete once you know the amount of force coming to these columns, and of course the load transfer to these beams when you have full load over this tank. So what we'll do in this course, we will learn the design of the new structural component, that is top dome, top ring beam, cylindrical wall, bottom ring beam, conical shell, and then spherical dome at the bottom. So these are the components. They are new, which was not encountered earlier, and hence in this discussion we will go through how to design them. Now let us first see what are the different geometric components and what are the different stresses we may encounter before we end up designing them. So it is an axisymmetric structure. If you look at plane, you'll see a circular wall. So it's made of reinforced concrete. The geometry ensures predominantly the membrane strain action that I have already explained, efficient load transfer, which is really required particularly for a large water tank having a really large mass at the top, and it reduces the bending moment. So the geometry that helps in reducing bending moments. Then let us first focus on the conical shell. So load transfer is efficient. It is effectively transferred to the ring girder and reduces direct tension on cylindrical wall, right? Then there is a spherical dome at the bottom. It reduces bending stress and the thickness requirement, right? Now let us first start with top dome. So it's a spherical shell covering the top of the tank. So that is the sole purpose. Usually the rise, that means if I draw this horizontal line at the ring beam level, how high it is at the middle. So this rise is normally 1/4 to 1/6 of the span. So the shell that we provide here, this spherical shell, it carries load primarily through in-plane forces and because of membrane compression. So to design this, we have to adapt the membrane theory for thin shell structures where stresses develop mainly in the surface. So it is a thin shell structure. So accordingly, we have to identify what are the different stress components that we'll do in a minute. Now, It transfers the load to the cylindrical wall. So effectively it will come here, and this ring beam also provides the connection between these two. So what are the type of membrane stresses available here at this section? Meridional stress, stress along the meridian, that is longitudinal direction, and then hoop stress. We are familiar with hoop stress. Earlier we have actually designed water tanks against hoop stress. So it is the stress that is developed that actually, if you have a load acting at the lateral direction, so that will produce a hoop stress and over this shell structure, and accordingly we have to design. Now let us first revisit the membrane stress. So for that, consider the dome as formed by a series of horizontal rings. So you can just imagine this is a ring, and if you circulate that along this center line, so then you'll basically get the top shell. So the dome is formed by a series of horizontal rings of decreasing diameters placed one above other. So you can imagine the diameter at this is maximum. Obviously, as we go towards the top crown portion of the dome, this diameter reduces. Now let us consider a segment, a ring. As you can see, if we can consider, say, a ring, small ring here. So this is the ring, and let us mark it D, E, F, G. Okay. And the radius of the ring and sphere are R and capital R. Okay. So at this level, radius is R. Okay. So when the dome is subjected to uniformly distributed load W per unit area, the membrane stresses can be determined from this geometry. Now we have meridional thrust is a compressive force acting along the meridian of the dome, right? It transfers load from the top of the dome to the supporting ring beam. So it goes like this. So to the supporting ring beam, it transfers the load. Meridional thrust increases towards the base. Obviously, the whole load is transferred to this ring beam. So as we go towards the ring beam, it transfers the full load and hence the full stress. As you can see here, the small segment that we have identified. Now, we can find out the area of the dome surface above the ring, DEFG, and for that we have this expression twice pi capital R times H. So H is marked here, which is the height above this portion DEFG. Now from the geometry, as you can see, we can express this H, which is equal to R minus R cos theta. So now we can evaluate the load above the ring DEFG, and obviously for that we have this area. So if we take R common and take it outside, so we have pi R square 1 minus cos theta, that is the area, and if you multiply by W, so we get the total load. This load is now transferred as the thrust on the circumference of the ring beam, ring DEFG. So the thrust per unit on this ring is capital T. So we are going to quantify this capital T soon. For that, total vertical component of the thrust on the ring we can evaluate, that is T sine theta times 2 pi R, that is the circumference of this ring. And obviously we can further simplify this because we already know the expression of total load acting. Now from this expression we can evaluate T, capital T, which is omega R, capital R divided by 1 plus cos theta. So what we get, meridional thrust, is this quantity. Now let us move on. The horizontal component of the thrust will act as hoop tension. So we can find out hoop tension, which is cosine component of the this capital T times r sine theta, that you can easily evaluate from the geometry. So capital H is omega r square times sine theta cos theta divided by 1 plus cos theta. So that is simple. We put the expression of T here and we get the desired expression for H. Now, similarly, the thrust on this ring just on its lower face will produce a hoop which is having a differential increment over the hoop force capital H. So the net hoop force is basically this differential increment, and area of the section on the ring is basically r d theta times t. So we can quantify hoop stress, which is this hoop compression divided by area, and we get sigma h as this expression omega capital R by t, t is the thickness, multiplied by cosine of theta minus 1 by 1 plus cosine of theta. Okay. So positive value of sigma h indicates compressive hoop stress. So we have quantified two things, meridional thrust and then hoop acting at that level. Now let us come to the top ring beam, which is here. So it is located at the junction between the top dome and the cylindrical wall. The horizontal component of meridional thrust at the dome base induces an outward push on the cylindrical wall carrying the dome. So obviously this force coming from the dome at the top will act on this ring beam accordingly. The horizontal component is resisted by the ring beam due to hoop action, and it is designed mainly for direct tension. We will see the design. Then once we reach this ring beam at the top, next is cylindrical wall. So it's a vertical wall for storing the water, and it is subjected to obviously hydrostatic pressure because this is filled with water. Then of course the governing stresses are hoop tension, which is again maximum at the base. Earlier also we have seen how to design this kind of vertical wall. So as we go towards the bottom, obviously the hydrostatic pressure also increases and the hoop tension. Now thickness may vary with depth because at the top the requirement of the thickness is less compared to that at the bottom. But for a efficient construction, we can provide same thickness. So the structural function is to resist the circumferential tension and then transfer the load to the conical shell. Okay. So here we have this shell structure. We'll see in a minute. Now, once we deal with this side walls, the cylindrical wall, the next structural component is bottom ring beam. So it is located at the junction. As you can see here, this is the bottom ring beam. So it raises the horizontal component of the reaction of the conical slab on the cylindrical. So we have the net force coming from here, and also we have the lateral forces. All these forces are actually resisted by this ring beam. Obviously the horizontal component is resisted by the hoop action and designed mostly to resist the hoop tension, because that's the main purpose of this beam. It provides sufficient strength against this hoop tension. Then we have component number 5, which is conical slab. It is a sloping shell connecting cylindrical wall to bottom dome. So this bottom dome here and this cylindrical wall, it is connected by this slab. Now again, it is designed for hoop tension caused by the water pressure, and then obviously here we will have some amount of bending moment for the span between the ring beam at its top here, which is number 4, and the ring girder at the bottom. So here we have a girder and there we have a ring beam. So in between that, because of this, it will try to bend. So there will be a bending action. Then comes the bottom dome, that is the component number 6. It is again a spherical shell forming the tank base. It supports water load and develops compressive membrane stress because of this spherical shape. And if you take a section, this is more like a arch, and if you rotate that arch about the central line, you will get this spherical shell. So it reduces again bending moment compared to flat bottom slab, which I have already explained. Now again, just like we had earlier for the top dome, we have meridional compression and hoop tension near the support. Then let us see the ring girder located at the critical junction between this side wall, which is slanted, and that we covered here. So it is a conical slab, and then the bottom dome. So this actually supports the entire tank load, and which is then transferred to the column. Okay. So obviously it experiences bending moment and torsion, and accordingly we have to design. Now, what is the structural function? It resists the horizontal thrust from the conical slab and lower dome, bending moment and torsion, and collect forces from the conical slab and bottom dome and distribute these forces uniformly over the supporting column. So then we see the force transfer to the column, and accordingly we have to design the column. Now, for the design, the bending moment on these ring girders, again we can go for a detailed structural analysis. For example, you can go for a finite element analysis for the entire structure and find out what is the bending moment acting on this girder. But there are some handy expressions already provided which we can use for the estimation of this bending moment. Now, these girders carry uniformly distributed load Wt, which is actually inducing moment. So the maximum negative moment at the support is C1 times Wt times R, and maximum positive moment at the midspan is C2 times Wt times R. Right. Recall, when we designed the roof slab, we had similar type of expressions that we used earlier. Now here, the maximum torsion for this beam will also be there, and for that we have this expression C3 times Wt times R. Now depending upon the number of supports, that means number of columns you have, that is here NC, we can have 4, 6, 8, 10, 12. We have, these are the values of C1, C2, C3. So from this table, depending upon the number of columns we have for the Intze tank, we can find out the respective values of C1, C2, C3. So our effective task is to estimate Wt, and we already know from the geometry the value of R. So we can calculate the moments at the support and midspan and also the torsion. Now, once that is done, we have to design against the bending moment at the support, design against bending moment at the midspan, torsion, and shear force near the support. Right. So these are the standard components for beam design. We will also adapt that for this ring girder. Now, the longitudinal reinforcement for the ring girder, let us see. For that, we have to consider the equivalent bending moment. So longitudinal reinforcement shall be designed to resist the equivalent bending moment, which is here. So you have already evaluated this components, and then we have to get this equivalent bending moment before we design the longitudinal reinforcement. And for that, we have, these are the expressions that we use, where TCG is the torsional moment, we have already quantified, MCG bending moment at cross section, then BCG is the width of the girder, and DCG is the depth of the circular girder. So when this condition is satisfied, longitudinal reinforcement shall be provided to withstand an equivalent moment of this quantity. For shear, we have, this is the expression, where again TCG is the torsional moment. So this is the additional component coming due to torsion. And of course, if this condition is satisfied, then we have to redesign the geometry, redesign the intersection. If it is not, then obviously we don't need to redesign. We can carry on with existing design. Now for transverse reinforcement, this condition needs to be satisfied. So that if this is satisfied, then we provide minimum reinforcement. And if it is violated, obviously we have to provide the area of stirrup, which is expressed by this expression, where SB is the spacing of the transverse reinforcement that we have to evaluate, and then B1 is the distance between the corner bars along width of the circular girder, and D1 is the distance between the corner bars along the depth of the circular girder. Sigma SB is the permissible stress in shear reinforcement, right? So let us sum up what are the different structural component: top dome, top ring beam, then we have the cylindrical shell here that provides the storage for the tank, then there is a bottom ring beam here, then conical shell, and then bottom dome. Then there are two ring beams, one at the top, one at the bottom, and of course below this we have the girders and then the columns, right? So that's how the load is transferred. So with that, let us close here today. In the next lecture, we'll take an example and we'll see how we design all these components and accordingly how we detail these structural components for this Intze tank. Please go through these slides. If you have any doubt, do let us know and then we will clear your doubt through emails. Thank you very much.